for safety and robustness. This work tries to estimate uncertainty for structured prediction tasks. Uncertainty in structured prediction, paper 2020, Andrei Malenin, Mark Gelas, abstract. Uncertainty estimation is important for ensuring safety and robustness of AI systems, especially for high-risk applications. While much progress has recently been made in this area, most research has focused on unstructured prediction, such as image classification and regression tasks. However, while task-specific forms of confidence score estimation have been investigated by speech and machine translation communities, limited work has investigated general uncertainty estimation approaches for structured prediction. Thus, this work aims to investigate uncertainty estimation for structured prediction tasks within a single unified interpretable probabilistic ensemble framework. We consider uncertainty estimation for sequence data and token level, complete sequence level, provide interpretations for and applications of various measures of uncertainty, and discuss the challenges associated with obtaining them. This work also explores the practical challenges associated with obtaining uncertainty estimates for structured prediction tasks and provides baseline for token level error detection and sequence prediction rejection, and sequence out-of-domain input detection using ensembles of auto-regressive transformer models trained with WMT English-French and WMT in 17 English-German translation and LibriSpeech recognition datasets. The contributions of these works are as follows. Firstly, this work examines uncertainty estimation for structured prediction tasks within a general probabilistic interpretable ensemble framework. We derive information theoretic measures of both data uncertainty and knowledge uncertainty at both token level and sequence level, make explicit the challenges involved, and state any assumptions made. Secondly, this work explores the practical challenges associated with obtaining uncertainty estimates for structured prediction tasks and provide performance baseline for token level and sequence level error detection and out-of-domain input detection and WMT 14 French and WMT 17 English-German translation datasets and LibriSpeech ASR dataset. Conclusion. Previously, uncertainty estimates obtained via a general probabilistic interpretable ensemble framework were examined for structured prediction tasks like image classification. This work investigates applying the same ensemble-based uncertainty framework estimation to auto-regressive structured prediction tasks. A range of information theoretic measures of both uncertainty at the token level and sequence level was discussed in section 3. It was shown that while token level measures of uncertainty can be derived in the same way as for unstructured predictions, predicting exact estimates of sequence level uncertainty is challenging. Two types of approximations were proposed. First, approximate sequence level measures of uncertainty are sum of token level measures. The other considers log scores of particular hypotheses to derive the measures like mean pointwise mutual information. In section 4, this work is explored the practical challenges associated with obtaining uncertainty estimates for structured prediction tasks and provided performance baseline for token level and sequence level error detection and out-of-domain input detection using ensembles of auto-regressive transformer models trained on WMT 14 French and WMT 17 English-German translation datasets and LibriSpeech ASR dataset. These initial results are promising and show ensemble-based measures of uncertainty are useful for all applications considered. Estimates of knowledge uncertainty were especially valuable for translation of out-of-domain detection. Additionally, many properties observed on unstructured prediction tasks carry over to unstructured predictions. However, additional properties were also observed. For example, with ensembles of ASR models are robust to out-of-domain inputs. NMT models can display pathological behavior such as confident copy-through with low ensemble diversity on the text from different language, adversely affecting the quality of uncertainty estimates. Furthermore, assessing the quality of uncertainty estimates for NMT via the sequence and token level error detection is changing due to the nature of the blue metric. Future work should investigate whether uncertainty estimates correlate well with the human judgments of the translation quality, explore better applications for sequence-level uncertainty, and consider alternative ensemble generation techniques. Furthermore, ensemble-based uncertainty estimates should be compared to the task-specific confidence estimates previously explored for ASR and NMT. Finally, the practical value of ensemble-based uncertainty estimates should be evaluated on large-scale ASR and NMT models used in production. Okay, so this was the juice, the spice of the paper that must flow. You got it now, and I will go deeper into the paper in following parts of the video. Please don't like and don't subscribe, and if you would like more, continue with this video. Okay, so introduction. Neural networks have become dominant approaching addressing computer vision, natural language processing, machine translation, speech recognition. However, estimating the uncertainty in enhanced prediction, which enables improved safety and automated decision making, is still area of ongoing active research. Notable progress has recently been made on predicting uncertainty estimation for deep learning through the definition of baseline, tasks, and metrics, and the development of Bayesian ensemble-based methods for estimating uncertainty, such as Monte Carlo dropout, deep ensemble, stochastic weight averaging, Gaussian. Uncertainty estimates derived using ensembles have been successfully applied to detecting misclassification, auto-distribution inputs, and adversarial attacks, and active learning. Crucially, ensemble-based approaches allow uncertainty to be decomposed into data uncertainty, which is intrinsic uncertainty associated with the task, and knowledge uncertainty, which is the model's uncertainty in a prediction due to lack of understanding of the data. Knowledge uncertainty is particularly useful for tasks such as active learning, adversarial attack detection, auto-domain input detection, where it is necessary to know the model is exposed to its input and does not understand. Despite recent advances, most work on uncertainty explanation using ensembles has focused on unstructured prediction tasks such as image classification. Meanwhile, uncertainty estimation within general probabilistic interpretable ensemble-based framework for structured prediction tasks such as language modeling, machine translation, and speech recognition, where model use variable length sequence of related targets y1 to yl has received little attention. Previous work has examined and developed bespoke confidence score estimation score techniques for each task separately. Recently, however, initial investigations into general uncertainty estimation for structured prediction have appeared. The nature of data uncertainty for translation tasks was examined. Estimation of sequence and word-level uncertainty estimates via Monte Carlo dropout ensemble has been investigated for machine translation. However, these works mostly focus on machine translation, consider only a small range of uncertainty measures, and provide limited theoretical analysis of their properties and do not make explicit their limitations. Furthermore, to our knowledge, our work has examined confidence scores estimation for auto-regressive sequence-to-sequence speech recognition model. This work seeks to address these issues. The contributions of this work are as follows. Firstly, we examine uncertainty estimation for structured prediction tasks with a general probabilistic interpretable ensemble-based framework. We derive information theoretic measures on both data uncertainty, the knowledge uncertainty, and both token and sequence level. Make explicit the challenges involved and the state of any assumptions made. Secondly, this work explores practical challenges associated with obtaining uncertainty estimates for structured prediction tasks and provide performance baselines for token level sequence error detection, out-of-domain input detection, and WMT14 English French, WMT17 English German translation datasets, and LibriSpeech ASR dataset. Uncertainty estimation via ensembles. In this work, we take a Bayesian viewpoint on ensembles and yielded elegant probabilistic framework which interpretable uncertainty estimates can be obtained. The core of the Bayesian approach is to treat model parameters theta as a random variable and place a prior over them to compute a posterior via Bayes rule. However, exact Bayesian inference is intractable for neural networks. It is therefore necessary to consider explicit or implicit approximation of q theta to the true posterior p theta condition on the data to generate ensemble of models. Number of different approaches to generating ensemble of models have been developed, such as Monte Carlo dropout, deep ensembles, and stochastic weight averaging Gaussians. Full overview is available in Ashoka 2020. Consider an ensemble of models sampled on approximate posterior, where each model captures unstructured mapping from x to y, where x is from data domain and y is from W1 to WK. Each of the models yields different estimate of the data uncertainty. Uncertainty in predictions due to knowledge uncertainty is expressed as the level of spread or disagreement of the models in the ensemble. The predictive posterior of the ensemble is obtained by taking expectation with respect to the models in the ensemble. Okay, so we take expectation of the probability conditioned on the data and the data. We get sort of the we approximate it using the ensemble. The entropy of the predictive posterior will be an estimate of total uncertainty. So the entropy. So how they do this? So they take entropy of the predictive posterior that was defined as an expectation over the probability of those different data based on the data, and the entropy is as expected an expectation of minus logarithm of p y of basically this posterior, this posterior model posterior. Total uncertainty in the prediction is due to both data uncertainty and knowledge uncertainty. However, for tasks such as misclassification detection, considering a log likelihood scores assigned by the predictive posterior to a particular class can yield superior performance. It is more sensitive to the prediction made. SCR is logarithm of p. Wait a minute. However, for tasks such as misclassification detection, considering a log likelihood score assigned by predictive posterior to a particular class can yield superior performance. Okay, so instead of doing using the entropy, we instead use log likelihood of the specific class of the model uncertainty. In certain situations such as active learning and auto-distribution input detection, this is desirable to evaluate uncertainty in prediction due to knowledge uncertainty. The sources of uncertainty can be composed of considering mutual information between the model parameters and the predictions. Okay. This is expressed as a difference between the entropy of the predictive posterior and expected entropy of each model in the ensemble. The former is measure of total uncertainty, while the latter is measure of expected data uncertainty. Their difference will be measure of the spread of the ensemble and an estimate of knowledge uncertainty. So we have total uncertainty and we subtract the expected data uncertainty and we get the knowledge uncertainty. Okay, it is also possible to consider expected pairwise KL divergence between the models and ensemble under a measure of diversity. This measure is an upper bound on mutual information and also allows total uncertainty to be decomposed into knowledge uncertainty and data uncertainty. Notably, only estimates of the total uncertainty differ, while estimate of the data uncertainty provided both decomposition is the same. Uncertainty for structure prediction. In this section, the probabilistic framework for uncertainty estimation discussed in previous section is applied to structure prediction. Let's consider models that capture mapping from X to Y between T-length sequence inputs and L-length targets. In this way, we consider auto-regressive. So there's a product of the probabilities of the certain Y conditioned on the previous outputs. In the model above, distribution over YL is a condition on previous. It shall refer to as context. This formulation describes neural machine translation and speech recognition and other related tasks. For these models, we will examine uncertainty estimation at the two levels. Token level, which considers uncertainty in prediction of a single YL given the context and input XL, and the sequence level, which considers the uncertainty of predicting the entire sequence Y given X. Token level uncertainty estimates. Token level uncertainty estimates for a model described by the equation are direct extension of uncertainty measured for unstructured predictions model discussed in section 2. By considering the mutual information between YL and theta, we obtain measures of total uncertainty, knowledge uncertainty, expected uncertainty. Yeah, I think that's obvious. But the sequence level uncertainty estimates. Having discussed token level measures of uncertainty, we now examine sequence level measures of uncertainty via ensemble approaches. Consider that while there is only one way to express the predictive posterior at the token level, sequence level predictive posterior for an autoregressive model can be expressed in two ways. First, it is expectation of the products. The other is product of expectations. Both are valid ways to do the Bayesian model combination. However, the optimal Q theta will depend on the choice of the combination approach. Consider Q theta, which maximizes log likelihood of a dataset under P in K estimation. If in this case, the optimal QK will maximize the joint log probability of all tokens in all sequences in the data D, but not necessarily conditional log probabilities of all tokens. In the latter case, optimal Q theta will maximize both joint and conditional probabilities of all tokens. Thus, Q theta is not general equal to Q theta tilde. This has two implications. Firstly, given set of samples of the model parameters for a particular Q theta, it is not immediately obvious what is the best way to combine models within an ensemble. Secondly, the choice of ensemble combination will affect the severity of any approximation given in the obtaining the measures of uncertainty. Having discussed the subtleties of the ensemble combination for autoregressive model, we can now consider how to obtain ensemble-based measures of the uncertainty, data uncertainty, and knowledge uncertainty at the sequence level. Let's begin examining mutual information between the model parameters theta and sequence Y. Evaluating this expression is more difficult than at the token level. First, let's consider the expressions for expected data uncertainty. This is simply average entropy of each model in the ensemble. However, evaluating entropy of autoregressive model is intractable due to the combinatorial exploration of the hypothesis space. There are total of k cardinality to the power of L, where possible L length sequences where k is vocabulary size. This is now necessary to do forward paths through the network for each hypothesis for all M models. Clearly, it is necessary to use some kind of approximation to make this tractable. One simple but crude approximation is to approximate sequence level entropy as a sum of token level entropies. Thus, explicit data uncertainty is approximated to the expectation of product of expectation. In neither case, evaluating the entropy is intractable, as that would require MK model evolutions. However, if you consider product of expectation ensemble combination, then the total uncertainty can be approximated as the sum of token level uncertainty via equation. Similarly, sequence level APKL also be expressed as a sum of token level. Knowledge uncertainty, first requirement, product of expectation of products, pointwise mutual information. This information theoretic measure of correlation of this particular combination of sequence omega and particular parameters theta. As PMI is defined in terms of P of Y condition on data, it is value that depends on whether it's obtained via product of expectation or an expectation of products. Note the mutual information is expectation of PMI across all possible hypotheses, model parameters. However, we do not have access to all possible hypotheses. The best which can be done is to take expectation of PMI across all models. This way, EPM is a measure of ensemble diversity, therefore knowledge uncertainty. However, while the measures of uncertainty considered above do not make conditional independence assumption, only examine probabilities assigned to a particular output of a sequence of models. And thus this main advantage is sensitive how well the models agree. Experimental evaluation tubes of ensemble combination, sequence level error detection. So experimental evaluation. Having discussed the ensemble-based measure of uncertainty for structure prediction tasks, we now provide performance baseline on free application of uncertain estimates, sequence and token level error detection, and auto-distribution input detection. This work, the uncertainty estimates are obtained for ensembles and regressing sequence neural machines. VM strategy decoding. Okay, I'm running out of time here. Sequence level error detection. In this section, we investigate whether the measures of uncertainty derived in section string can be used to detect sentences which are challenging to translate or transcribe using NMT and ASR respectively. In the following experiment, the model hypotheses are sorted in order of decreasing uncertainty and incrementally replaced by the references. The mean sentence blue or sentence WER is plotted against the fraction of the data replaced on rejection curve. If the uncertainty estimates are informative, then the increase in blue or decrease in WER should be greater than random linear. Rejection curves are summarized using prediction-rejection ratio. The results are provided in table 5. Table 5, sequence level error detection prediction ratio decoding scheme. So, total uncertainty, data uncertainty, knowledge uncertainty, TU-SRPE. Well, I would have to get into the descriptions. Okay, token level error detection, auto-distribution input detection. Examine tasks of sequence level token level error detection now is considered OD input detection. The goal is to measure the uncertainty of the discriminate between in-domain test data and out-of-distribution dataset. Performance is assessed via area under ROC curve, where 100% is the area of ideal performance and 50% is random. Anything below 50% indicates the perverse situation where the model yields lower uncertainty for the OOD data than for in-domain data. And above 50% performance can be achieved by negating the uncertainty measure. Results are presented in table 7. Okay, I'm not getting this 100%. So this is it. Ran out of time now, so I will read few first lines of conclusion. Previously, uncertainty estimates been obtained via general probabilistic interpretable ensemble framework were examined for a structured prediction tasks like image classification. This work we investigated applying the same ensemble-based uncertainty estimation framework to auto-regressive structured prediction tasks. The range of information theoretic measures of uncertainty both at the token level and next sequence level was discussed in section 3. It was shown that while token level measures of uncertainty can be derived in the same way for the unstructured predictions, obtaining exact estimates of the sequence level certainty is challenging. Two types of approximations were proposed. First, approximate sequence level measures of uncertainty as a sum of token level measures. The other considers log score of particular hypotheses to derive measure like mean pointwise mutual information. In section 4, this work explored practical challenges associated with obtaining uncertainty estimates for structural prediction tasks and provided performance baselines for token level and sequence level error detection and out-of-domain input detection using ensemble of auto-regressive transformer model trained on WMT English-French, WMT English-German translation dataset, and LibriSpeech ASR. These initial results are promising and show that ensemble-based measures of the uncertainty are useful for all applications considered. Estimates of the knowledge uncertainty were especially valuable for translation OOD detection. Additionally, many properties observed on unstructured prediction tasks carry over to the structured predictions. However, additional properties were also observed. For example, while ensemble of ASR models are robust to OOD inputs, the MMT models can display pathological behaviors such as codefinite copy-through with low ensemble diversity on the text from different language, adversely affecting the quality of uncertainty estimates. Furthermore, assessing the quality uncertainty for NMT via sequence and token level error detection challenging due to the nature of the blue metric. Future work should investigate whether uncertainty estimates correlate well with the human judgment of translation quality, explore better approximations for sequential uncertainty, and consider alternative ensemble generation techniques. Furthermore, ensemble-based uncertainty estimates should be compared to the task-specific confidence estimates compared to performance MMT. Final practical value of the ensemble uncertainty estimate should be evaluated on large-scale SR and MMT models used in production. Thank you very much. That's been all. You made it to the end. Big surprise. I hope to see you next time. Please don't like and don't subscribe. See you.